Hello, my name is Brandon Montemiro, and I'm a postdoc at the University of Washington. And I will be talking about SubZero, a new discrete element sea ice model with an explicit representation of flow life cycles. And this is part of a larger MURI project researching the mathematics and data science of sea ice, which has been funded by the Office of Naval Research. So I'd like to start off with a little background on these scales of Arctic sea ice, which is one of the challenges that sea ice modelers face. Starting off with the microstructure of sea ice at the crystalline scale, which are 1 nanometers, and the grains are at 1 millimeter in size. Zoom out a little bit more, and you start seeing the air and brine pores in sea ice, which are at 0.1 to 1 meter in size. When we start looking at the flow scale, we see thermal cracks appearing at 10 to 100 meters in size, and the individual ice floes themselves can range anywhere from 100 meters to 10 kilometers in size. These range of flow ice scales are seen here on the right in an image from the Nares Strait, where we can see some of the really large sea ice flows and some of the real smaller ones next to each other. And then when we zoom out even more, we start looking at the basin scale. This can include things such as the Beaufort Gyre, which can be 1,000 kilometers across. And on these scales is when we start seeing the large kinematic features such as leads and sea ice forming. And then this just wide range of scales with different physical processes that happen on these different scales present a very tough challenge for modelers of sea ice, both on the discrete element side as well as continuous side of sea ice modeling. Today, we're going to focus on the discrete element models. Historically, discrete element models use bonds between particles. These are point particles or spheres, which are connected to each other via normal and frictional forces, and these bonds can break. There have been a range of different methods used to implement these bonds. These can include level sets, circular elements, as well as polygonal flows. Some of the challenges associated with these existing models can include different problems such as all the elements are fixed in shape. It can be hard to identify what an individual flow is with some of these different methods. And it's also can be difficult to decide what do the point particles actually physically correspond to in observations. And so to try to address some of these issues, we have developed at the University of Washington our discrete element model that we called SubZero. And the goal is develop a model that is capable of simulating the life cycle of physically observed flows such that the model physics could be validated using direct measurements at flow scale. And when we're talking about the life cycle of physical flows, we're talking about these different physical processes that a flow can go throughout its life. And so we have here on the bottom left, 3 elements that are next to each other. These elements can then weld together to form one larger flow. And then if there's enough fracturing and stress, this individual flow element can then break up again into a couple of new flows. And so to describe our model in a little bit more detail, we'll start off here with the flow evolution equations. These represent the conservation of momentum, both linear and angular momentum. The first term physically represents forces from oceans and atmospheric stresses. The next term physically represents the flow-flow interactions that are involved in the model. And lastly, there can be forces from unresolved flows. At the time being, these are not incorporated in our model, but we hope to include them in future iterations. And so to resolve these flow-flow interactions, we need to describe our contact laws. So with SubZero, we allow for non-convex polygons. And the way we find our forces between the flows is we find the overlapping region between the 2 flows, and then we use this to determine our normal forces, and then the frictional and tangential forces can come from these overlapping regions, as well as incorporating the velocities of the 2 flows involved. And then to represent the entire life cycle of our flows, we have incorporated a couple different physical processes to parameterize these. And so we start off with the fracture of flows. So if a flow, we find the forces through these contact laws. We then determine the stresses that the flows are undergoing. And then depending on those stresses, if certain criteria are met, the flows can then fracture into multiple smaller pieces. Next is the specific type of fracturing, which we are calling corner grinding in our model. And what happens here is that the corners of our flows represent regions of increased stress. And since the stress is concentrated in these regions, they are more prone to be fracturing. So when the flows are interacting with each other, there's a certain probability that a sharper corner will then fracture out the flow, forming more rounded shapes because older sea ice typically is more rounded in observations. Next, we have welding of two flow elements. So when there is an overlap area as shown here, under proper thermodynamic conditions, these flows can actually freeze together and form one larger flow. Or if the flows come in contact to each other, there is a certain probability that we will have a ridging incident where mass will then be transferred from one flow to the other, and one flow will have its shape updated while the other one will retain its original shape and just have gained mass from the other flow. And then lastly, we have the ability to create new flow elements. And so there are two different times that we can run this creation of new elements algorithm. The first time can be to initialize our model run. And so we can take an image shown here, perform image segmentation, and take some of those flows that we can identify and use those to start our model. But the other flows, we might not be able to identify the individual flows. So using Voronoi tessellation, we are then able to populate the rest of the image with these more original shapes, and then try to match the concentration of the image. The other time that we can run this creation of new elements algorithm is throughout a model run. We might periodically run this because under certain thermodynamic conditions, say it's wintertime, we know that we want to try to maintain our model at approximately 100% concentration. And so we will identify the open ocean and then populate this open space with new flow elements. And incorporating all these physical processes allow us to then model the entire life cycle of a flow. And now that we have our model set up, we want to run some validation cases. And we start off with the Nares Strait. So the Nares Strait is a region between Canada and Greenland. And then as shown here, in the winter, this fills up with sea ice. And then in the spring and summertime, these sea ice will break up and move through the strait. It is a region of interest because here there's a lot of multi-year sea ice that can then move through the Nares Strait and exit out of the Arctic Ocean. And now with SubZero, we have the capability to analyze flow size and thickness distribution as they propagate through the strait. So we would like to ultimately use satellite data to validate our model and compare the flow size distribution as well as the ice thickness distribution with our model with that of the observed flow amounts. And so with our model, we use two immovable and infracturable flows. Those are the flows in green to create our boundaries for our sea ice to move through. The blue arrows represent an average ice velocity over a certain amount of space, showing how ice is moving with time through the strait. And ultimately, as I said, we will run this for a longer time and compare our flow size distribution with observations. Our next test case is winter. And so what we're doing here, we have idealized forcing with a quad gyre shown in the red arrows. We then incorporate all of our different physical processes that we mentioned, which includes fracture, ridging, rafting, welding, and the creation of new flow elements. And we run this throughout time with no winds, the idealized forcing of the quad gyre. We also have double periodic boundary conditions, so the flows can move in and out of the boundaries, appear on the other side, and then we use ghost flows to find the interactions with them. And what we're searching for is an equilibrium of winter sea ice characteristics. We want to see if this is achievable because of all the different physical processes going on. If fracturings are occurring too often, our number of elements can go to infinity, or if welding is happening too frequently, we could end up with just one large flow. And so we want to see if we can achieve an equilibrium that is also realistic with observations. And then what we can see here is after we run it for a long time, we have this puzzle shaped, which is qualitatively similar to this SAR image from the right, where the white is the thicker sea ice. The black is very thin sea ice that is frozen in, giving this puzzle fragmented nature, which again qualitatively looks like our image. And so looking at the statistics, we can see that we have achieved a steady number of flows. This occurred in roughly 1 week of simulation time. There is this sawtooth nature to our number of flows, which comes from periodically it dropping off due to welding, and then the creation of new flows, which fills in the open space and can freeze together some of these smaller flows into one flow. And then later, the number of flows will increase due to fractures. Lastly, we're looking here at our flow size distribution on the left. We have this minus 2.6 slope for our power law, which is within the realm of observed power laws for flow size distribution. We have this flattening off at the top. This comes from, we have a minimum flow size where when the flow drops below this, we no longer fracture the flow to save computationally. And we can see here that we also have our flow size distribution. We keep reaching an equilibrium value very quickly within our realistic flow size distribution power loss range. Then on the right, we have our ice thickness distribution. Our model was initialized with everything being at 0.25 meters ice thickness. So we had a delta function there. And then over time, due to the different flow interactions, mass being transferred between the others, and thermodynamic growth, we have started to approach a gamma distribution, which is what is observed for sea ice. So the future of SubZero, we have a number of different things we would like to look for. One, we want to see what happens with a full Arctic-wide simulation, and this would involve moving to a conglomerate of flows with rescaled interaction laws. Shown in the red square is the Nares Strait, so that is the flow size that we were initially creating the model with, and as I stated at the beginning, due to all the different flow scales, it can be difficult to tell what will happen with the model, how realistic would be, and so we just kind of want to run this and see how does SubZero do with these large scales. We also want to look to couple with an ocean model such as Oceananigans to explore the ice-ocean interactions at the flow scale. And then we also want to look at the super parameterized sea ice model, which would involve a combination of macro scale equations and the microscale DEM. This is part of the larger MURI that I talked about being a part of, and looking at the mathematics of sea ice. So in conclusion, we have created a model which can simulate the evolution of sea ice flows. We have our preliminary validation studies of sea ice have shown a realistic behavior of the flow size distribution and the ice thickness distribution, and the opportunities for sea ice research with SubZero are endless. If you want to find out more, follow us on Twitter at CICemath, or check out our website, cismuri.org, and see what our entire MURI is doing. Thank you.